Okay, so welcome to day 12 of Advent of Code. Um, as usual, we have about 12 minutes, so let's reflect on how day 11 went. Um, Day 11 was a fairly straightforward problem. Um, and I would say it all went well, except I had a silly little bug in writing my neighbor's function again, which is just, given an x and y coordinate, finding all the adjacent coordinates. Um, and as we talked about on the previous day, I hate that function. Um, and so maybe like grids of digits in particular, and maybe numbers in general, because we did bingo cards much earlier on, maybe grids of numbers are going to be a thing. Um, I actually wrote a little library to help working with grids of numbers. Um, the most notable thing is just because we had been using arrays of integers of length 2 to represent coordinates. Um, okay, I bit the bullet and created a real struct called point two. Um, we can use that, and um, well, um, the most important thing that we can do with that is actually down here. Is that now any two-dimensional array we can subscript with a two-dimensional thing, which just does y first and then x as subscripts. It does require a little bit of kind of Swifty magic to build that extension, because you have to make sure that both of these things, that both your outer and inner sequences are random access and can be accessed and can be indexed by int. So that's what these clever where clauses are all about. But I also added this function here as grid, which is meant to be to parallel the enumerate function that all sequences already have. Because when you enumerate something, you get like a counter. You get a tuple that returns you a counter and the value. So you can kind of go 0, 1, 2, 3, 4, 5, 6 with all the values next to it. This will give you similarly tuples that return you a point 2D and the element. So you can iterate over an entire grid, getting its coordinates and the value at that coordinate. And the way we do that is, I build this kind of custom iterator thing that keeps track of where it is, and it doesn't do anything clever. It really is just a matter of, every time you do every time you get a point, you just increment x, and if you go past the end of that row, you just, go to the next row. But we use clever Swifty features like this guard thing is kind of the nice way to not add a level of indentation with an if. And we use defer is actually a really, really beautiful part of Swift that lets you execute code after the return statement. And defer is kind of, it's just an example. Swift is a modern language, not modern in the sense that it's adding a whole bunch of crazy new stuff that we don't know anything about. But I think Go has a very similar statement, and when I used Go, I was impressed by it. It was super useful, and I'm sure there are other more experimental languages that it first showed up in. But having spent a lot of time in older languages, C and C++, and even Python, it's really nice to use a language that has been designed in the last few years, and so takes advantage of everything we've learned from all these other languages. Swift doesn't have a yield statement, which is like a crazy useful feature that Python has. But yield strikes me as having quite a complicated and heavyweight implementation. I'm not quite sure how they're doing it in Python, because you got to preserve an entire call stack and everything. But anyway, putting all that aside, so what can we do with a point two? We can index a two-dimensional array or any kind of two-dimensional random access integer addressable thing with it. We can iterate across an entire grid. And I wrote 3 versions of this neighbors function that has driven me crazy for the past couple of puzzles. One that gives you all 8 of the neighbors. One that gives you just the Manhattan neighbors, just the 4. And one, I have no idea whether this would be useful, but it's the toroidal neighbors, which is effectively you assume that both the x and the y-axis wrap around. So if you go, so the things on the left edge are adjacent to the things on the right edge, and the things on the top are adjacent to the things on the bottom. And that is topologically equivalent to a torus. So I wrote those functions. And then, after I wrote all this stuff, I realized that actually this only works for random access collections. And so if you have a grid, but of anything, integers, characters, whatever, but the trouble is if you have just an array of strings, I have added a subscript operation that lets you subscript a string by integer. But of course, strings themselves aren't really random access collections, and I assume this is because internally they're encoded probably as UTF-8, and so you can't actually jump directly to the character. You have to actually scan over each character to get there to know how many bytes you're using to store it, so it's not a constant time operation, so it's not technically a random access collection. So my index by number is potentially inefficient, or at least it's linear in the size of the linear in the offset that you're going to, which I assume somewhere it's documented that random access collections is supposed to be constant time, right? So what I just did is I copied all this stuff and I just said, hey, it also works for string protocols as well, so we can do it on strings. And I mean, I wouldn't say that any of this is terribly robust code, but I have written very rudimentary tests for all this stuff. And it's not that I have good test coverage, but just having somewhere you can hang new tests as you discover bugs is a huge amount better than having nowhere to hang the test. Because if you fix a bug and you don't have anywhere to hang a test, you're not going to write this framework to add a test if you don't have a place to put it already. So I think just having a place to put your tests is useful. I also wrote a couple of things in the input, really just wrappers around one-liners. Oh no, those are tests, hold on. The input. These are just a couple of one-liners that can read, this digit grid is what we had been doing the last couple of days, just a square of individual digits. And this other one is just numbers separated by white space, like the bingo card that we did. Again, I don't know if either of those is going to come up in another Advent of Code thing, and it is only a one-liner, but it might prevent us typing it if we remember the interfaces to these things, which is half the problem with writing a library, is you have to remember exactly what the API you decided on was. So, oh, sorry, you probably can't read this. Let me make it bigger. So, the 2 functions I was talking about are just down at the bottom. Digit grid takes an array of lines and turns it into a 2-dimensional array of integers, and similarly for the number grid. So, let's go back to our reflections. What else did we say? Oh no, so I wrote that library, and if you rewrite our part 2 solution, which is over here on the right, using, well, I didn't actually use the digit grid up at the top. But if we rewrite this thing on the right, using our new library, well, this neighbors function goes away pretty much entirely. So really, the equivalent thing starts with this flashes thing. It's not a huge amount less code, but it is a lot cleaner, because now you're using real positional coordinates. You don't have to do a lot of this kind of line noise, multiple subscripting and yada yada yada. It's just a little bit cleaner. Is it a big deal? No, no, not really. But, you know, I wrote this version just to see what it would look like, and I do think this would have gotten us the solution faster and would make bugs more evident because there's less noise in doing all this stuff. And of course, assuming I wrote my neighbors function at the library correctly, that was the only bug we had yesterday, is that I wrote neighbors incorrectly. So we wouldn't have to do that this time. Anyway, what else did we learn yesterday? I mean, this wasn't completely obvious to me at the time, but of course, once everything in the grid is synchronized, then they're going to stay synchronized. They're just going to flash every 10 steps. And so I should have realized that and just bailed out of the whole thing as soon as we synchronized once. So that is pretty obvious once you think about it. And similarly, if you think about how long could it possibly take for everything to synchronize, well, you're going to synchronize with your immediate neighbors in 10 steps. 10 times 10 steps. You're going to synchronize with your immediate neighbors, right? Because they're going to catch up to you by 1 step per cycle. So after 10 cycles, your immediate neighbors will have caught up with you. And so in theory, propagating all the way from one corner to the other could take 10 times 10, but, you know, it doesn't quite work that way because all the neighbors are going to be synchronizing with each other. So I didn't work out what the absolute maximum time it could possibly take for everything to synchronize would be, but in general, it will only take a few hundred steps. Certainly wouldn't take thousands. So, how are we doing on time? Okay, well, let's stop reflecting and actually get started on day 12. Here we go. Come on. Okay. No digit grid this time, it looks like. Okay, so pairs of strings split by whatever. Lines map. Zero split based on separator. Okay. So we're going to end up with pairs of strings, I think. Find the number of distinct and don't visit small caves. Big caves and small caves. So we're not doing shortest paths. We're doing any kind of path. Weird. How many paths are there? Well, oh, it's not a very big cave system, is it? So interesting. So if it's not a very big cave system, we could just try every possible path and see whether it's possible, right? In that case, let's just say next is a dictionary from string to set of string. So this is where you can get from somewhere else. Next. Come on. Now, is this going to go in? Is set so are we taking a copy of S, or are we inserting into the one that's already in the dictionary? I'm not sure. There's a more efficient way to do this, but I don't want to bother trying to remember the correct syntax. So the second part of that is right. I don't know about the first. So let's see if we got any of that right. Come on, run. Nope. Oh. I really hate substrings in Swift. Oh, no, still not getting anything right. Come on. Wow, a lot of things wrong. Did we 1, 2, 1, 2? We did the same thing yesterday with our syntax. What? Oh no. Cannot use mutating. S is a let constant. Yeah, that's true. But we're never. Yeah, that first one is not. This is very not efficient. Next. Oh, 0. That's looking better. Okay. So we know where we can get from where. And let's actually just get all the rooms. Okay, so we have all these rooms. What do we want to do? So we want all the possible paths. Oh, come on. That's not what I meant to do. Your goal is to find a number of distinct paths that start at start, end at end, and don't visit small caves more than once. So how do we do that? We try to go, at every stage, we try to go everywhere, right? And we have to keep track of visited. Okay, so explore, and we have let's say that's our path is an array of strings. And visited is a set of strings. And we return a bunch of pads. Okay. So, start. Okay, so nope. If not visited contains then and we're gonna have to build up our thing. So if no, let's do that. I could have saved that text, really. I'm very slow at this stuff. So if it doesn't contain n, then new path. If n is end, then otherwise, let's keep exploring, right? Equals explore with the new path, and we do need to update visited. Yeah, that looks good, but we gotta update visited. So if not, so what is this? How do we tell if everything is a capital? Transforming, excluding, selecting, finding, removing all. There's some kind of all function. If a predicate is true for everything, remove. Yeah, all satisfy. There we go. So, if not all, or actually, if all satisfy, what? This is n. All satisfy. And what does it take? 0 is lower. Is this what we know about characters? then, oh no, not that. Then, oh, insert, and there we go, and we will call that with nuv. So then so we don't need that anymore. Let's actually use output because it's there. Explore. Just start with that path and set. Empty set. Well, let's see if this compiles. Start. No, of course it doesn't. Why would it? Oh no, only 2. Missing visited. There we go. We knew that because we named it. What else? Foreign 23. In next. Or what is the right hand side? Is a set of strings. Oh. Is low. I knew I didn't remember this. So well, let's come on. We go to string, and then from there to character. Come on, give me a link. Where's the link? Give me a link. Where's my link? You can go much here. Well, click here, and then click here. And now we have ASCII is lowercase. That's what it's called. And where was that? Is lowercase. No. Oh. Maybe we shouldn't have named this. Oh no. Not you. No. Trailing closure is confusable. Pass is parenthesized. So was this a named argument, or can we just do this? Is that how it works? Well, it compiles. Good for us. Let's always print the path. And it didn't find any. Is it because it starts with begin or something? Let's, what was our input? Start. 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 Okay. For n in next. What? Print next. JF Oh, are these bidirectional links? I think that's her. Yeah, these are bidirectional links, I guess. So. Okay, if var. Let's just do this all a second time. And flip the ones and zeros. There's a more elegant code structure, but this is probably faster to do, right? Ooh, whoa. So we got a whole bunch of things, which is nice to know. So certainly don't need that. We might have duplicates, so let's set of string arrays. Wait, what is this? That's not right. Let's see if this compiles. Whoa, well, it's the kind of number, my intuition says that's too high given how small our data is, but let's see, because it's the kind of number that Advent of Code likes, but it's not. Okay, so what are we doing? Okay, suppose this is our input. Then, let's so we got 37, and they only have slightly larger example. There are 10 pads through there, so let's print our output. Start. We should definitely put start. Wait. Yeah. Let's put start into it. Come on. Print output. $10. Okay. Should we try the bigger? There are 10 paths. Here's a slightly larger example. Yes, we might as well do the slightly larger example. No, you. Here we go. 19 paths. Okay, so I think we got this. So our bug was we didn't put start in the thing. Okay, that matches my intuition for the order of magnitude of the answer a little bit better. And we got it. Okay, so let's do our thing. because we're not being fast anyway, and see what we have in part 2. Most twice. A single. Okay. How many paths? So how do we tell if we're visiting a single cave twice? Do do do. So let's. So, and we have to format our code within 80 characters. Doubled. Okay. If we didn't visit it, okay, we can do that. We're just going to cut and paste because we know this code works. Else, okay, we know that we visited this, so we're just going to do this all. Oh, yeah, that's good. Else, if not doubled. Okay. Now, do you think we should take a stab at this? Well, yeah, let's see if we got it right before we do anything with the test data, because test data is boring. No, okay, let's try the test data. So, through the first example. Oh, sorry, wrong window. Okay. This is the smaller example. I like that he gave us 2 examples. So we say 63. And he says 36. Why is that? Doubled, false, double, true, double, doubled. Okay. I guess we need to, you know what, let's it's easier to read by line, so let's actually see what all these things are. You can never visit start twice. It says that in the problem. Else, if not doubled, and is not equal to start. get? 36, is that what he said? 36. Let's try that on our real input. Yeah. I'm guessing most of the time is spent spitting out all these print statements that I could have removed, but yeah, okay. So we got there. Couple of minor bugs just because we didn't read the problem as carefully as we could have, but okay. Day 12 was fun. So I'll see you here tomorrow to reflect on day 12 and to do day 13. So I will see you then.